Okay, I picked up some information from the last problem, which I'm sure you're all eager to be done with, okay? But we had this one critical point that happened to be a location of a min. Our other critical point wasn't a max or a min, but this one was a location of a min. And we used that as our test point for the sign of the second derivative, and we saw that it was positive there, which meant that we were concave up. And that illustrates something that's called the second derivative test. So here's the basic idea. If C is a critical number for f, and it would have to be one such that f prime of C is equal to 0, because I'm going to need to be able to take the second derivative, and if C was a critical number because the first derivative didn't exist, then the second derivative wouldn't exist either, and we wouldn't be able to use this test. If you can't use the second derivative test, you always fall back on the first derivative test. But what I'm going to do is I'm going to take that critical number and I'm going to plug it into the second derivative. And there are four possibilities. That could be positive, that could be negative, it could be 0, or it could be undefined. And I'm going to see what that tells me about classifying C. So let's see. If it's a critical number so that the first derivative is 0, I know I have a horizontal tangent. But if the second derivative is positive, I know that my graph is concave up. Now there is only one point on the graph of something that's concave up at which I have a horizontal tangent, and that's at a min. So C would be a location of a min. And that's exactly what we saw here. Here was our critical number that was the location of a min. The second derivative was positive there, so that we were at the bottom of that smiley face. Okay. If the second derivative is negative, that would tell me that f is concave up. But if the first derivative was 0, I've got to also have a horizontal tangent. There's one and only one point on the graph of something that's concave up where there's a horizontal tangent, and so this would be a location of a max. So if I have a critical number and I want to classify it to know whether it's a location of a max or a min, neither, I can try to plug it into the second derivative rather than using the first derivative test. A couple of drawbacks. Obviously, if the critical number is one where the first derivative doesn't exist, we can't do this. If the second derivative ends up being 0, that's not going to tell me anything. And if the second derivative is undefined, that's not going to tell me anything either. In this case, the test is inconclusive, but we don't just say, oh, I don't know. We use the first derivative test. So the first derivative test works every time to figure out whether a critical number is a location of a max or a min. As a general rule, it's my go-to, because I've got to take the first derivative anyway in order to find my critical numbers. And it's not too difficult usually to create this number line, and I know it's going to work. Whereas the second derivative test doesn't work every time. It just works some of the time. Okay. So you might say, why do we even bother teaching it? Well, I think it's kind of a cool theory to see how the concavity relates to whether it's a max or a min. But if you're planning to take 3C, this is incredibly important. Because in 3C, you're going to start to have functions where you've got a two-dimensional input and then a one-dimensional output. Put that together and you've got a graph in three-dimensional space. Okay. When you're trying to find maximum and minimum values there, the first derivative test does not generalize to that sort of function, but the second derivative test does. So the theory is very important when we move on to a couple semesters from now and some more complicated sorts of functions. Okay. If I ask you to find the location and value of the relative maxes and mins of a function, you can do it however you want. I don't care whether you use the first or second derivative test, provided that if the second derivative test is inconclusive, you know to fall back on the first derivative test. But I could specify. I could say, find the location and value of the relative max and min using the second derivative test. Okay. So let's suppose we've got f is equal to x minus the square root of x. And that's what I want to do. I want to find the location and value of the relative max and min if they exist, but I want to classify it using the second derivative test if possible. Okay. All right, I will just point out that with the square root in here, my domain is just everything from 0 to infinity. Okay. It's not going to be a problem because I'm not going to get anything that's negative, but if I did, I'd have to say, nope, not in the domain. Okay. All right, I'm just going to rewrite this as x minus x to the 1/2. So I need to start by finding the first derivative. That's going to be 1 minus 1/2 x to the negative 1/2. And I'm going to need to see what my critical numbers are. So this is going to be 1 minus 1 over 2 root x. Okay. Now, that is going to be undefined at 0. So if I want to know what happens at 0, I would have to use the first derivative test. Although, if I said we were looking for relative maxes and mins, I can actually say, nope, because 0 is an endpoint, and relative maxes and mins can't occur there. Okay. So, any critical numbers that I have would be where this thing is equal to 0. So that would mean that 1 is equal to 1 over 2 root x. Multiply that over. That's going to give me 2 root x equals 1. Root x is 1/2. So x is 1/4. Okay. So my critical number is c equals 1/4. I'm going to plug that into the second derivative to see if I can classify it to see whether it's a max or a min. Okay, so here was my first derivative. If I take the second derivative, that's going to give me 1/4 x to the negative 3/2, or 1 over 4 times the square root of x cubed. So, if I evaluate that at c, f double prime evaluated at 1/4 is going to be 1 over 4 times the square root of 1/4 is 1/2 cubed. That's going to be 1 over 4/8, which is 8/4, which is 2. And I probably could have stopped a while ago because I could tell it was going to be positive. There was no way I was going to get something negative. So then I have to say, okay, so if the second derivative is positive, what does that tell me? And it's really easy to get the wrong answer at this point because I tend to think positive, oh, big stuff, maximum. What I want to think is positive means concave up. So if I remember to just draw that it's going to be concave up, I can see from the shape of that that this has to be the location of a min. So f has a relative min when x equals 1/4, and the value of the min is f of 1/4, which would be, let's see, plugging into the original function, 1/4 minus the square root of 1/4 is 1/2, so a fourth minus a half, which is going to give me negative 1/4. All right, so that's how the second derivative test works. Do make sure that you know that test so that I could ask you about it. If you got a critical number and the second derivative is positive, what do we know? Or I could ask you to use it. But generally speaking, like I said, if you're finding maxes and mins, you're probably going to be content just to use the first derivative.